So, dear ladies and gentlemen, I feel the most sorry to interrupt this beautiful Mozart sonata, which also connects to the place where we are, Vienna. And it's my pleasure to announce the last plenary talk of Symmetry Festival 2016 Vienna, which will be given by the chairman of the executive board of International Symmetry Association and the professor of physics of University of Hartford, US, Larry Gould. And the talk, Albert Einstein, Myth and Magic, connects, I think, on many ways and on many levels to all the physics-related talks and many other talks in symmetry studies that we had here in this meeting. So I'm very happy to have this beautiful summary of our conference as well, and I give the floor to Larry. Thank you.
Thank you. Is this on? Oh, I should turn it on. How's that? Yes. Can you hear me?
Good.
Yeah. You can hear the tap. Now you can hear me. Okay, good. So, as Kristóf said, this is Mozart. Why do I play violin music at the start of this? Because Einstein played the violin. He liked to play Mozart too. So what I'm going to try and do is give you some idea of an extraordinary individual, Albert Einstein. Is there anyone here who has not heard the name Einstein? Okay, yeah, that's the usual response that I get. I gave this talk once at a public library, not the same, an earlier version of the talk. And there are people from retirement community. And in the Q&A, someone told me that she knew someone who became a minister who was in Princeton. And as a child, his family befriended the Einstein family when they moved to Princeton. And he drove Einstein around. So he wrote a wonderful article, which this woman connected me to. And the title of the article is Einstein from the Rear View Mirror. Okay? It's a very entertaining article. Now, Einstein is very well known, and what I would want to give you an example of is just what's in a name. You know, Shakespeare, what's in a name? A rose by any other name. There's no other Einstein as far as I know, but what's in Einstein's name, all of the things that have gone on in his life through his discoveries and through his interaction with the various world events. So I want to give you a flavor of what he discovered, what the significance was about what he discovered, and also some of the myths about Einstein. You know, you have some famous people, and they sort of take on a life of their own in the minds of the people who are aware of them. And so a lot of myths come out as a result. I'll show you some of them. Okay. I gave a talk similar to this at a college in my area, and this person says he has this wonderful picture of Einstein on the cover of Time magazine, and this says Cosmoclast Einstein, and all matter is speed and flame. Okay, that's what's on here. All matter is speed and flame at the beginning. What does that mean? I don't know. I mean, matter certainly has speed, and maybe flame has to do with energy. A cosmoclast, I know, iconoclast is someone who, to class is to break, and so cosmoclast is something like the breaking of the universe, maybe, you know, or penetrating into the heart of the universe. Okay. Einstein is celebrated not only on the cover of Time magazine, but also on stamps. And I love some of these stamps. You know, this one over here, this is from Italy. It looks like one of the Italian composers, you know, conductors, not Stokowski. No, that looks like Stokowski. That's the Polish one. And then we have something from the USSR, which used to exist. It's around here somewhere. The DDR also. Here's the DDR. That's no longer. Okay. Now, some people think that, well, the height of human civilization is with Einstein. So here we are on the way up the ladder of civilization. And then we get 2 equals mc squared. And then what happens? Well, it's all downhill from there. Supposedly. I don't think that's true, but sometimes I wonder. That's where we're heading. That's downhill. Okay. Now, so I think that really is one of the myths. But then we have loads of books written by Einstein. And if you want to find out some really good insight about Einstein, get it from the horse's mouth. This is Albert Einstein, philosopher, scientist. There are 2 volumes by Schilp, and this is, as far as I know, it's the only autobiography of Einstein. And for the people who read German, it has the German on one side and the other, the English translation on the facing page. Now, if you look at Einstein over here, you know, in this next picture, he has leathery face. You know, this is a typical picture of Einstein. Leathery face, gray hair, you know, wide eyes, very elderly gentleman. And so one of the questions is, was Einstein ever young? Now, of course, the answer is yes. And here he is as a teenager. And another question might be, was he short? I used to think that he was short. My wife thought he was short. He was around 6 feet, a rather tall gentleman. If you see him in pictures, and you know the height of the other people, you can get a good idea. Here's another question. Did Einstein believe in God? When I was an undergraduate, there was someone who's giving a talk. He was a theologian, and he was referring to Einstein. Einstein is a believer in God. It's a little more subtle than that, actually. Here's Einstein's position about God. What he thinks of in terms of religious feeling is a cosmic religious feeling which knows no dogma and no God conceived in man's image. Okay? Instead, it comes from a deep conviction of the rationality of the universe and a yearning to understand and to experience the universe as a single significant whole. Now, Peter Achenstein actually was talking about the ways of knowing or believing in the simplicity in the laws of physics, and this gives you some idea of Einstein's view about what is the universe like, that it can be understood. Okay? Now here's another myth. The myth was he was very bad in school, and then he blossomed. Not only did he blossom, he bore many fruits. Okay. Did he do poorly in school? Well, you might reflect this in, if he did, something like this. This is supposed to be, there's Einstein's first equation, 3x is 12, x is equals 6. Okay? That shows you he did poorly in school. You put 6 in for the people who don't know much math. Put 6 in on the left side, you get 18. So 18 is not equal to 12. Okay. Well, let's look at his school grades. Age 6. Yesterday, Albert received his grades. He was again number 1, and his report card was brilliant. Okay. What sort of grades did he get? Well, one of his teachers said that he will never get anywhere. Well, actually, he didn't get anywhere. He got everywhere. Right? I mean, his name is known throughout the world. Here's an idea of some of the grades. You look at German, French, he got a 5. The marks, 6 is excellent, 2 is very poor, and 1 is unusable. I guess that means it can't be used in the university. Maybe they kick you out. I don't know what the grades are in German. But you notice that in geometry and physics, he got 6s, top of the class. Okay. So that knocks out that myth about Einstein didn't pull in school. He was very impressed by by experiment. People think, well, Einstein's just a theoretical physicist. Actually, he was very familiar with the experimental literature, and that is very important because you just don't theorize without any input. Okay? And I think it may have been Minkowski who said that the physics springs from the world of experience. And what is seen here is what early apparatus was around the time that Einstein was a student at the Technische University, the Technical University in Switzerland. This thing over here is a resistor, it's a variable resistor. Actually, I remember seeing something like that when I was an undergraduate. Yeah. He was very impressed, you know, you hear the story of the compass needle, okay? And his uncle brought him a compass, and there was this invisible force. And he was fascinated by that. And another example of invisible force, in particular fields, electric and magnetic fields, was developed by first Faraday, the early part of the 19th century, and then James Clerk Maxwell picked up on the imagery of that Faraday communicated. Because Faraday was very unskilled in mathematics. Maxwell, on the other hand, was very skilled in mathematics. So he formulated the mathematical equations that captured the ideas, the main ideas from electricity and magnetism at the time. From that, he found by manipulating the equations, you get something which are called wave equations. And the waves that are propagated were a new kind of wave. They were electric and magnetic waves that were propagating electric and magnetic fields. Okay? And there was an ether that was believed to exist, just like water waves require material, a medium, water, in order to get waves. Air is the medium for sound waves. So there's something called the luminiferous ether, which enabled electromagnetic waves to be propagated. And about 10 years after Maxwell died, Heinrich Hertz actually verified the existence of electric magnetic waves. Now, if this is a little abstract to you, cell phones work by means of electromagnetic waves. Communication between here and the rover on Mars, or communication by other objects, radio stars, giving rise to signals that we receive on Earth. And in fact, and this is the amazing thing about Maxwell's discovery, is that the speed that he found for these electromagnetic waves, he said he noticed that is extremely close to the speed of light. So he says probably light, there's good evidence that light is electromagnetic nature. Maxwell discovered the nature of light. Okay? And from then on, we have not what's called the usual rainbow of colors, we have what's called Maxwell's rainbow. And so it includes the electromagnetic spectrum by which we see all the colors, but also beyond the spectrum to infrared, to radio waves on one side, and to X-rays, to gamma rays, to ultraviolet rays on the other side. And Einstein didn't know all of the radiation at the time. This is 1905 when he was doing his work. But Maxwell opened the door, and this is the reason that Einstein was so impressed by Maxwell. So Einstein was heavily involved in physics and studying literature, but life was not only physics. Okay. He married Mileva Maric, who was a student also at the time that he was at the same place at the Zurich Polytechnic, and they had a child. Hans Albert was the first child, and there was some question about, was she involved in the creation of special relativity? Well, they probably discussed it over the dinner table, but in terms of the actual contributions, there was something in Physics Today some years back, and the evidence is that, no, she didn't make any seminal contributions to special relativity. Now, here's another myth, Einstein the theorist. I already indicated that he read the literature, the experimental literature, but he worked at the patent office. Okay? So he was judging in 1905 in the patent office in Bern. He was judging whether a particular idea is patentable or not. So he had great familiarity with how ideas connect to the world. Okay? And in theoretical physics, you're not doing theoretical physics unless there is some indication that your ideas can connect to the world. They have to be tested out, for example. There was a professor of his, Weber, who he got angry with because when Einstein wanted to do an experiment to measure the velocity of light, Weber wouldn't let him do it. Okay. Now, this next is an image of a patent that Einstein got with Szilard. And it was a patent for a refrigerator. Okay. And it used metals, molten metals. This was after the time that Einstein worked in the patent office. He worked in the patent office, among the years, there's the famous year, the Annus Mirabilis, the year of marvels, or it could be said the year of miracles, or the year of magic, to connect with the title. And this is a picture of him when he was at the patent office. During one year, in 1905, he came up with some rather remarkable ideas. One was demonstrating molecular reality. There were huge debates, even though the ideas of molecules was used in the 19th century, there were still huge debates whether there exist these tiny particles that you can't see. Well, Einstein already was keen on things that you can't see anyway, because you can't see electric and magnetic fields. So, but he wanted to show that you can perform experiments which would verify that there are these objects, these which we call molecules or atoms. And he had a PhD thesis which pertained to this, and he published a paper on it. And we have gone rather far in the meantime. After Einstein, we can now see the atoms. These are arranged in a layer. These are individual atoms. I think they're silicon. And when I say we can see, you can't see them with the human eye. You can't look at them under the most powerful microscopes. But you can look at them if you're clever and invent a microscope that does that. So just if you have these bumps over here, you can think of as the atoms, and in between the bumps, think of roughly as spaces. And if you have a bunch of ridges, or if you run your finger over your other fingers, you can feel the individual fingers. So this is something on a microscopic level like that. and the atoms give rise to electrons, which go into this thing over here. That's the probe, okay? And then the picture goes to a screen, and you can see where the signal came, and that's where the atoms were. You can see that on the screen. And this particular device is called a scanning tunneling electron microscope, and the reason is because quantum mechanics comes in and actually enabling this thing to work. From waves to particles. Remember, Maxwell's theory talks about electromagnetic waves. How do particles come in? Well, Einstein knew quite well about gas theory and the ideal gas law, and he found that there's a certain relationship between, I think, entropy and volume in the ideal gas law, how the entropy changes with the volume. And in the enclosure, which contains electromagnetic radiation, he worked out that the entropy also should change with the volume. So he said, aha, okay. Well, on the one hand, we know the ideal gas law. Well, if they're particles of gas, then, and they exhibit this characteristic of, say, the entropy changes with the volume, and the same kind of thing happens with electromagnetic radiation, which is supposed to be continuous, then maybe there's a particle aspect to it. But that's not the end of the story, because there are experiments. For example, I mentioned Hertz earlier, who verified Maxwell's theory experimentally. Hertz discovered that during the verification, there was an emission of charge. There was a current that was contributed by light that was blue. Okay? And the only way you can explain the certain aspects of the emission is that you need something other than the wave theory. Because in the wave theory, the energy is spread out. Okay? So if you turn on the light and you want to see a current, and you say, well, how long will it take for the current to be generated if you turn on the light? I did the calculation roughly. Other people have done it, plenty of people. Students could do it. Okay? It takes about a minute. Actually, you turn on the light, it's also almost instantaneous. And the way you can explain that is not by the wave theory. There must be some concentration of energy in the waves. And that's where the particle aspect comes in. That's where what we call photons comes in, or the corpuscular nature of light. Now, or the photoelectric effect, this actually was a paper that came before the paper that was what we call the special theory of relativity. And it's, in English, the heuristic viewpoint concerning the generation and transformation of light. Heuristic, so this explains the events. This was Einstein's title. Here's the German. And this, you notice, Annalen der Physik, 1905. Okay. I'm going to point out the date for each of these things. Some of the applications, garage door openers, cameras, the pixels, the light strikes the photodetectors. In experimental physics, there are photodetectors. So you have light, which is emitting electrons, that is producing current. Okay, and the best way to understand it is by thinking of light as particles. Then comes the next situation. I would call it life on the fast side. Fast side, special theory of relativity. It's the fast side because you're not used to observing things that travel near the speed of light. And the special theory of relativity fundamentally depended on experiments to detect the motion of the Earth through the luminiferous ether that I mentioned earlier. Okay? And the strange thing about it Okay, I give you one really simple example. Okay? That it's very counterintuitive. It took me actually some time before I could really believe in the special theory of relativity, because I wasn't keying into the key postulate. The key idea is this: if I'm traveling toward you at 60 miles an hour, you see me coming toward you at 60 miles an hour. If I throw a ball toward you at 30 miles an hour, then what do you see the ball coming toward you at? 90 miles an hour, right? Okay. If I threw it even faster, you see the ball coming at you faster, okay? Now, if I change the ball into a particle of light, and I'm at rest with respect to you, and I shine my flashlight, you see the particles of light come at you at the speed of light, 186,000 miles per second, 3 times 10 to the 8 meters per second. Okay. Now, if I'm coming toward you at half the speed of light, then the question is, well, what's the speed that you see the light coming at you? And the answer is not the sum of my speed plus the light speed. It's exactly the same as if I was standing still with respect to you. Now, anything is counterintuitive. I think that's a great example of something that is counterintuitive. Nevertheless, that was the basis for one of the bases of the special theory of relativity, because they couldn't find in the experiments this kind of naive idea of the addition of velocities that you would expect. Okay. So, electrodynamics of moving bodies. The title of the paper was not the special theory of relativity. It was electrodynamics of moving bodies, or so elektrodynamik bewegte Körper. I think there should be an umlaut over the O. There should be. I just got it. What are some consequences of special relativity? Length contraction. Okay, length contraction, if there's a meter stick that's moving past you, okay, then if I'm moving past with a meter stick, I see it at 1 meter, you see it at less than a meter. That's called length contraction. Time dilation. So if I have a clock and my clock is going tick, 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 then what you hear when you see it, or what you see the clock doing, is tick, 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 tick. That's time dilation. Dilation means to expand. Okay. Then there's a twin paradox. People like the twin paradox. The idea is you have 2 twins there on Earth. Okay, one goes off in a rocket ship, very high speed, for some years traveling to the speed of light, comes back and then meets his twin again. And this time, however, the twin on Earth is much, much older. Okay, so there are cartoons about this. And this says, if Einstein, these people are returning to Earth, if Einstein's is correct, when I get back, my car will have been double parked for 320 years. Energy mass equivalence, E equals mc squared, another consequence of special theory of relativity. Okay? And what I like to use here to capture the idea, try and capture the idea, is I would call it relativistic billiards. Okay? And it's relativistic billiards. When you think of ordinary billiards, you fire one billiard ball into another billiard ball, and they go off in some direction. You have 2 billiard balls, though, coming in, 2 billiard balls going out. In relativistic billiard ball, you have 2 billiard balls coming in, you have 4 billiard balls coming out. And why? Well, E equals mc squared. If there's a certain amount of energy that goes into slamming the billiard balls together, then part of that energy goes into mass. And in certain conditions, some of the mass turns up as a new particle. One of these particles, however, in this case, if you slam 2 protons together, is an antiproton. So you might say it's relativistic anti-billiards in billiards. That's one of the consequences. And what I was saying before, you don't experience things near the speed of light. This line over here indicates something about what you should see when you're below the speed of light. And so this is this ratio. This is at the speed of light. This point. This is about 2/3 the speed of light. So when you're very close to even the speed of light, you don't see the effects much. Special relativity comes up though. when you're near the speed of light, and particle physicists use it all the time, you know, high energy particle physicists. Okay, the speed of light, it can give you, to get a feel for the speed of light, if you sent a little particle of light around the Earth's circumference, it would go around 7 times in 1 second. That gives you an idea how fast the speed of light is. Yeah. So that's the relativistic field. Energy, equivalent of energy and mass, okay? You see here, 1905, okay? That was the later paper. So you had you had molecular reality, you had the photoelectric effect, then you had the electrodynamics of moving bodies, special relativity, and then you had E equals mc squared. You look at E equals mc squared paper, very short. Very short, because he says, well, if you go back to this paper on the electrodynamics of moving bodies, that's where the idea comes from. And by the way, his argument is a symmetry argument. He talks about collisions and what happens after the collision. There are symmetry effects in there, which I don't have time to go into. Okay. Now here you see L over V squared, okay? This is actually the disguised form of E equals mc squared, okay? Except L stands for energy, okay? Now I'm not sure what he meant what the German word is. It might be Lichtstrahlen for energy, and V over here. The capital V is the speed of light. Okay, that's what we use. Now it gets transformed. You see over here. Now the L is crossed out, and you have an E. I don't know whether this is an original discovery of mine, or whether probably I think people like Jürgen Renn and other people know about this. And then you see C is in place of capital V, and C I think stands for celerity or quickness. Okay, this is here's the E equals mc squared again. This time I want to play it for you. This is Einstein talking about E equals mc squared. No.
It follows from the special theory of relativity that mass and energy are but different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is cut equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kochler and Walton in 1932 experimentally.
Okay. And E equals mc squared, by the way, that was used in producing the nuclear energy that's used in the nuclear generating power plants for electricity. And also E equals mc squared comes in what's called fusion, the energy that the sun is producing. There isn't a bunch of wood up there that's burning. It's actually a different kind of process. It's burning wood is a chemical process. This is a nuclear process that E equals mc squared is applying to. Okay, now getting back to the social side, was Einstein a pacifist? Okay. I heard that Einstein was a pacifist. He was a pacifist in the First World War, but things changed in the Second World War. He knew about what was happening in Germany. He knew about the concentration camps and the horrors. Okay. And he, by the way, never went back to Germany because of what has happened there. And in fact, this letter, you can't read it. I don't want you to read it. It's a letter that was written by Szilard, and Einstein signed it. Okay, so Einstein was vacationing on Long Island. This is during the Second World War, and Szilard was driven by Edward Teller, and they couldn't find Einstein's house, so they asked a little girl. And she says, well, I don't know who this Albert Einstein is, but there's this kindly white-haired gentleman that lives down over there. That was, of course, Einstein. And what this letter is about is alerting Roosevelt to the fact that the Nazi had access to large amounts of material from which you can get the uranium from which you can create an atomic bomb. And so he's suggesting that we get going on a project, the United States. Okay, on to wave mechanics. This is maybe not too well known to people. That is the quantum mechanics and special relativity connection. Louis de Broglie, I think it's called de Broglie, but no one can understand what you're talking about. Louis de Broglie used Einstein's special theory of relativity as an essential ingredient to conclude that what we consider to be particles, like electrons and protons, actually have waves associated with them. So this is the reverse of what Einstein had done. Einstein said, well, you have waves, electromagnetic waves, and they have a particle-like aspect. De Broglie said, well, you have particles, and they have a wave-like aspect. That's a very important discovery in quantum mechanics, which was then later on picked up by Ernst Schrödinger, and he came up with what's called the wave equation. So Einstein has now made quite a name for himself with the discovery so far. This is a Solvay conference in 1911, and I would like you to notice where Einstein is. Here's the Einstein, the young man. He's off to the right over here. And there are some famous people. Here's Marie Curie, for example. Next comes another year of marvels, 1915, the year in which general relativity is created. And this is the manuscript, which he gave a number of his papers to the Hebrew University in Jerusalem. And this is the foundations of general relativity. And the paper is here in the Annalen de Physique. Okay? So this is no longer 1905. This is now 1915, 1916. And these are some of the equations, which, needless to say, perhaps I'm not getting into. Okay. Here's another myth. An interesting sideline is that Einstein called his introduction to the cosmological constant the biggest mistake of his life. Okay. Now the story isn't even apparently isn't true about Einstein saying that. Apparently it comes from George Gamow. Okay? And it wasn't the biggest mistake of his life. He was doing just what a physicist should be doing. At the time, there was no evidence that the universe was expanding, that the galaxies were flying apart. So he said, as beautiful as my theory is, I have to put something in to accord with the evidence. Okay? He didn't need it. Okay? But nevertheless, he was just going along with the observations. And then later on it was put in, now it's related to issues of dark matter. So. Okay, consequences of general relativity. Bending of light ray by the sun. Now, in Benno Wilke's talk, he was talking about gravitational lensing. Okay? And so you have massive objects that create gravitational field, and light from distant stars or distant objects can bend around it. So here's what you have. There was an observation to determine whether general relativity's prediction about pi bending is correct. So you have it's easier. you see over here, this would be the apparent position of the star. Okay. So if the sun wasn't here, you would see the star, at this position. But if you have a solar eclipse, okay, most of the light of the sun is blocked out, then you can actually see the stars near the limb of the sun. And you need to be near the limb of the sun because that's where the gravitational field is strong enough to deflect the light beam. And when that happens, then the light bends and it goes in this direction. Now it's a characteristic of the brain and the eye system, so they use telescopes. But it's the characteristic that when you see a light coming in, your brain and eye think that it's coming from the backward extension of the ray. So the star appears to be here. And if you take photographic plates of where the stars appear without the sun being close and with the sun being close, you see that there's a shift of the stars position. Okay, and actually the way you do it, you look at the other background stars, and you find out that there's a shift with respect to the other background stars that are far away from the sun. And the precision wasn't great, but it indicated that you can get the shift. By the way, you can also get the shift if you use Newtonian gravity along with special relativity. You think of light as energy, but it also has mass. If it has mass, it should be affected by gravity, okay? And you get a calculation, and I do it actually in my special relativity course, as an exercise for the students. You find out that the value that you get for the deflection is half the value that is observed. So part of the value that's observed comes from the warping or the curvature of space-time. So another consequence of general relativity is the advance of Mercury's perihelion. So the planet goes around the sun like this. If it was just the sun and Mercury, it would go around in a nice ellipse. But as a result of the gravitational effects, the ellipse turns. Okay, so the ellipse first is in this position, and so on. Okay. Now most of that effect, about 5,000 seconds of arc, comes from the perturbation of other planets in the solar system. However, 43 seconds of arc rotate per century. That rotation of the perihelion, that comes from something that people couldn't explain. They thought there was another planet, I think it was called Vulcan, okay? But they couldn't find the other planet. However, general relativity predicts this extra 43 seconds of an arc. There's a gravitational redshift. Because light comes off, when it leaves a body, it actually decreases its wavelength, so the tired light coming off an object. There's a prediction then that light should be redshifted if it comes off a gravitational body, particularly massive stars. And what they tried to do is find out this effect to detect it at the Einstein Turm in Potsdam, Germany. Actually, I was there, I visited there. Someone by the name of Janke, who was a physicist now, took me there. This is years ago. And they couldn't detect the general relativistic effect because it was mostly special relativistic effects that they could see. So it didn't work, but they could throw an image of the sun on an underground screen to try and observe the effect. But it didn't work for general relativity. It was a good idea though. Okay. Another consequence is black holes. And both Sasha Husa and Benno Wilke talked about black holes earlier in the conference. And this is a nice artist drawing of black holes, supposedly light entering a black hole. And you can't see it, as you know, what Benno told you. It's a hole, so light comes in, doesn't come out. So you don't see it, so it's black. Okay? And it's a hole because it doesn't come out. Okay? So let's see, consequences of general relativity, the bending of light by the sun, the advance of Mercury's perihelion, the gravitational redshift, black holes. the gravitational radiation, this I had to add into my slide because of LIGO, and that you heard about from Benno Wilke and Sascha Husse. Okay? This was the first direct detection of gravitational waves from two massive black holes colliding. And then the cosmology, the expansion of the universe, general relativity pertains to that. As far as the evidence goes, the universe is expanding and it will keep expanding, so energy will be dissipated and the human race will become extinct. Not for a while though, you know, billions, I don't know how many billions of years. By that time, we'll probably figure out a way of working around the situation. This is just a little poem, you know, about the people who still want to go with space as Euclidean. So, can you read it? These concepts, new and shiny, and Riemannian Einsteinian, because Einstein used Riemann's ideas, are much too brave and bold and fancy-free. It leaves me quite unnerved to find that space is curved. What was good enough for Euclid is good enough for me. On the way to the laser, someone by the name of Bose sent Einstein a paper where he used statistics in analyzing how light behaves. I won't go into details. Einstein read the paper, liked it a lot, got it published, and then went beyond it. He said, well, it's true for light particles, but light particles have no rest mass. You can't be at rest with respect to them, you can't weigh them. However, what about other particles? So there are these things called bosons, certain pi mesons particles have this characteristic. And so he took the Bose statistics and he applied it to these particles. And these days, it's called Bose-Einstein statistics. Graduate students learn about it all the time. This is Bose. Okay. Now I want to show you, we've come through relativity, okay? We've come through the photoelectric effect, we've come to the applications, the consequences. And I showed you a picture of Einstein at the Solvay conference back in 1911. Okay, now I'm going to show you a picture of Einstein at the Solvay conference of 1927. Okay? Now where is he? Now he's dead center, right? And this is Lorentz. Here's an older Marie Curie. Everyone's older, of course. This is Schrödinger. Okay, and there's Born and Rutherford and other people in there. It's like a who's who of physics. So now the question is, how did he do it? How did Einstein do all of these things? Okay. Here's one possibility. E equals ma squared. No. E equals mb squared. No, that doesn't look too good. How about E equals mc squared? Ah, that looks right. Now, of course, that's nonsense. That's not the way he came at it. But it's a nice cartoon. Well, the way he did it, he was able to sniff things out. He said, I soon learned to, this is from Einstein, I soon learned to scent out that which was able to lead to fundamentals. There are all these phenomena there in the world. You know, you can spend your lifetime on one small area. How do you get to the essentials? How do you get to new ideas of space and time? How do you get to things where you have done better than Newton on the second law of motion, and you've done with special theory of relativity, and you've done better than Newton in the universal law of gravitation with general relativity? How do you do that? Okay, well, you have to have a good nose. So here's a picture, and this picture is Albert Einstein, or the nose as a thought reservoir. Now, I don't know if anyone knows about this, but you know, after Einstein died, they got his brain, and they were starting to analyze the brain. You know, how many creases over here? Does that tell us anything? And so on. And they found some things, but apparently they were looking at the wrong part of his anatomy. They should have been looking at this instead of in there. That's a bad joke, okay. So I'm almost at the end here. This is my favorite photo of Einstein. Einstein the dreamer. Einstein the visionary. Einstein the benefactor. And who's given us so much, he's given the world so much. He was just interested, as he said, he has an intense curiosity about things, about the world. And as a result of that, the world has benefited in its advanced technology that we have today. And what I'd like to end with here is a touching tribute to the work that's meant so much for human civilization on this planet that we call Earth. This was a cartoon of one man's estimate of Einstein just after Einstein died. It's the Earth. Albert Einstein lived here. So, thank you for your attention. Oh, fourth.
Thank you very much, Larry, for this beautiful, wide talk, which really shown us or led us into Einstein's cultural universe as well, not only the scientific universe. And you certainly help us to deconstruct some myths, but you also contributed to construct new myths on Einstein. And now it's the time for questions and comments. Okay, the first was Jan.
I missed a picture
Yeah.
dressed as a lady. I missed a picture. Einstein was dressed as a lady.
Einstein was. Okay, yeah. Well, that may be another myth. I'm not sure. I've never seen that one.
There are several.
There were several. Einstein is dressed as a lady.
Yes.
Okay. Well, I know my father did it, but I didn't know that Einstein did it. Okay. Maybe I can locate that. One summer I was working at the Einstein archives at Caltech, and I was working on a paper with one of the editors there. I was still working on it, Hillman Sauer, and he showed me around, and I got to look into the archives. But it's probably huge archives. And,
On the internet you can find it.
Okay. You have to be careful of the internet. You have to be really careful. That's where a number of these myths come from. So I'll have to check it out. Yeah.
Okay. The second hand in the air was by Wolfgang Hofkirchner.
Thank you. Just a comment to what you said. I missed another photo, the photo where he showed his tongue. I think this is very popular, and the most popular for me, because I was educated after the 68 revolutionary students situation, and so this was a very famous photo for us.
Yeah.
But I wanted to add something else. I wonder why you did not mention that there was seemingly a third period in pacifism of Einstein, because he signed this so-called Einstein-Russell Manifesto, by which
The Einstein? Sorry.
Russell Manifesto, and this was the document in which they founded the Pugwash movement, and which was really a very important thing and something which we miss today.
I know that Einstein was involved with the peace movement. I just didn't have time to mention some things in the talk. I'm aware he was associated with the atomic scientist, I think the Bulletin of the Atomic Scientist earlier. Yeah, well, thank you for calling it to other people's and to my attention.
I'm Mr. Tompkins, and I arrived from the fantasy of George Gamow. So I would like to put you two questions about two myths which you didn't mention, but are very popular myths about Albert Einstein. The first is the statement of Albert Einstein, who once stated that he didn't know about the publication of the transformations by Lorentz, which have been published a few months before his famous paper on the on the relativity theory. The second is about the correspondence between David Hilbert and Albert Einstein, which they changed the letters in the autumn of 1915 about every second day between Berlin and Göttingen. And what was the impact, the real impact of David Hilbert to the final formulation of the general of the so-called Einstein equation, on which Einstein worked already about 7 or 9 years, and Hilbert was involved in the last year.
Okay, so what is? You wanted me to comment?
So what is the truth and what are the myths in these two?
Okay, so what the first one was? Just remind me briefly. What was the first one?
Einstein stated that he didn't.
Oh, the Lorentz transformation. Okay, I got it. I remember. Okay. Yeah. What I know about the Lorentz transformation, I don't know whether Einstein knew about the Lorentz transformation, but even if he did, okay, even if he, whether he did or didn't, the situation about the transformations, one can get some information from Lorentz himself. In this little book, The Theory of Electrons, there are appendices, a huge number of appendices. And one of the appendices, Lorentz comments on what are called the Lorentz-Einstein transformation equations. And what Lorentz says is that when you have the time transformations from the time in one inertial system, as seen by one observer, to the time of an event as seen in another inertial system. For Lorentz, one of the times wasn't the time; it was just a symbol. Okay. For Einstein, both of those had physical meaning. One was the time in one frame of reference, and the other was the time for the event as seen in another frame of reference, like the time for a lightning flash as seen by me at rest or as seen by someone else moving with respect to me with a constant velocity. So for Lorentz, there was no physical meaning to one of the times. It wouldn't be called time, but in the Einstein sense. In Einstein, that was one of the tough parts of the formulation, by the way, in special relativity, was to understand the issue of time. In fact, he interacted with Besso, who was a lifelong friend, about this issue. Okay, so that's what I know about the time thing. And then the other was the Hilbert. Yeah. So there's a wonderful talk on video, you can get it on YouTube, by Jürgen Renn. He's in Berlin. Who's a historian of science, and there's also an article in the Physics Today. And there was Hilbert, who came up with a variational formulation, a certain mathematical way of arriving at Einstein's main field equations. And that was done before Einstein. And then there was some friction between Hilbert and Einstein. Einstein was concerned that Hilbert was trying to get credit for general relativity, but that was smoothed over, and Hilbert said this was Einstein's result. So that's what I know about. And that I learned from watching Jürgen Wren video. What? Oh, yeah.
I have several comments. First, I would like to thank you for this interesting talk. Very nice. I enjoyed it. Now, making some remarks about this time Lorentz transformation. For Lorentz and the others, except Einstein, there was always still this Newton absolute time, and going to a reference system that is uniformly moving introduced this, as you said, an artificial time. But still, on the basis was this absolute time. It was always also relative to this absolute time, say relative to the eta or whatever you want to call it. This was one argument. The other argument about the equations that Einstein published, derived, and the controversy with Hilbert, you mentioned it. To my knowledge, it was so, and I mentioned that in my talk, is that it was in was November, wasn't it? November. Was it, Hilbert sent his paper to Einstein 1 week before Einstein filed in his paper, and in that paper there's a certain controversy whether the exact equations were already there. There was this variational principle that you mentioned, which guaranteed Hilbert that the equation would be generally covariant, this symmetry I talked about. So, and the controversy, I think, is still going on, a controversy between Wren and a lady scientist in Göttingen. It is known that Hilbert modified his manuscript when he get what is it called? What is it called in English? The proofs. When he got the proofs, he modified his paper essentially, and it's not clear what the modifications really were. Were the equations in Hilbert's paper or not? But this paper is so difficult to read that Einstein, it's believable that Einstein could not work through that paper within 1 week and get his equation. So Einstein had a completely different approach, and as you said, Hilbert at the very end said, no, it's all your theory. And sorry, one last comment. You mentioned the cosmological constant, and I think the biggest blunder or not. And you mentioned that one of the arguments of introducing the cosmological constant is that you wanted to have a static universe. That's correct, and this was one of the issues. But there was another issue which I also mentioned in my talk, is the so-called Mach's principle, Mach's idea. Einstein wanted that his equations only have solution if there's matter, if there's one. And for that, it was the second reason for introducing the cosmological constant, then assuming that his equations would not have solution without matter. This was a mistake, as it turned out. But this was very essential, what he called the Mach's principle. There shouldn't be any space-time without matter.
I believe you mentioned the empty matter solution in your talk, and you also pointed out Emmy Noether, and that, for the people who weren't here, or to remind people, Emmy Noether was the creator of the mathematics of the variational principles, which were then used by Hilbert Noether. I know that in 1915 there was a very intense period pertaining to general relativity. Einstein gave a talk once each week at the Prussian Academy of Sciences, and finally the last one was the correct equations. He was struggling toward the equations. But thank you very much for your comments. Yeah.
Okay. We have time for 2 more short questions or comments.
I think it's good to mention that another legacy of Einstein is the famous paper by Einstein, Podolsky, and Rosen in 1935, about the nature of quantum reality. This is one of the most cited papers at that time of Einstein, and it's still, let's say, an open question to know if Einstein was right or wrong. At least Bohr didn't agree with Einstein, and he said that quantum mechanics was a complete theory. But at the moment it's still a very active field about the interpretation of quantum mechanics, and specifically it has to do with a new era of quantum technology related to quantum bits and other things, quantum computer and so on. I think it is useful to mention this important work of Einstein.
Yes, I know the Einstein-Rosen-Podolsky paper. Einstein was involved in controversies about quantum mechanics, and I quite agree with you. There are these different interpretations. In fact, I had given a number of lectures about one of the interpretations called the Bohm interpretation, but there are others. The Copenhagen interpretation is Bohr and Pauli, and Schrödinger is more, I think, was more in the Einstein camp with the interpretations of quantum mechanics. That is, I think that at the bottom there's the question of, well, do you remain content with just probabilities? Because the wave function of quantum mechanics is a measure of the probability of an event, or do you look further, or do you look for what? Okay, a coin comes up heads or it comes up tails. Why does it come up heads or come up tails? What if it doesn't? What if it comes up heads most of the time?
So, ladies and gentlemen,
look further, you find, well, it's a loaded coin. You know, it has more weight on one side. So that's the kind of that's one of the issues I think that comes up in interpretations of quantum mechanics. And as you mentioned, it still goes on today. They have conferences. So thank you for the comments.
The last question or comment.
Yes, this is a comment where you mentioned several consequences of the general theory of relativity, and you mentioned the first, that the sun bends the way of the ray. It is true, but the consequence is that every mass which is on the way of any ray of light makes the same. And it was the first experiment with this eclipse of sun, which made Einstein the most famous man ever. So the consequence does not concern the sun; it concerns every experiment of such kind. That was the first.
Yes. Well, we've had Peter Eichelberg, Benno Wilke, Sascha Husse have talked about other objects that bend light rays besides the sun. You're quite right. I mean, anything that's gravitational, that has mass, has some gravity associated with it. The question is, can you detect the effect of the object? And it depends on how strong is the gravitational field. So for black holes, you have some significant effects. For neutron stars, for white dwarfs, you have significant effects, gravitational field affecting bending of light. Yeah, so you're right. There are a lot of things, many things that...
Many astronomical observations.
Yeah, sure. Absolutely.
Confirm this idea.
Right.
Oh. So thank you very much for Larry for leading us to this beautiful legacy of Einstein as the last parallel session, last plenary session of the Symmetry Festival. And you can see that the lunchtime also became relative during we have some consequences, but the conversation will continue during the lunch, and we are collecting some power and energy for the last panel discussion, which will start from 2 o'clock, when we will take one more step towards the unknown, and we will explore connections between relativity and the arts in the same room here from 2 o'clock. The moderator will be Larry Gould, and the panel members of this discussion are Professor Rauch and Renate Quarenherberger and Kay Hamburger and György Darvas. So welcome back at 2 o'clock in this room. Thank you very much for your attention.